Hello everyone, and welcome to today's lecture. So today we'll be talking about word embeddings, essentially how the map words into vector spaces to try to capture semantic meanings of these words and the relationship between them. So we'll discuss how these embeddings are learned, the different ways to generate them, and their practical applications. So the central idea behind word embeddings is that we want to learn a mapping function, let's call it W of any given word, that takes a word and converts that into a high-dimensional vector representation. It could be, for example, 64-bit or 256, whatever we decide. This mapping should allow words with similar meanings or usage to be close together in the vector space. So instead of treating words as isolated entities, embeddings should capture relationship between them based on the context. So let's look at some properties of word embeddings. So one of the most exciting properties of word embeddings is that the relationship between words often correspond to the difference between their vector representation. So for example, if you look here, the vector from man to woman should be similar to the vector from uncle to aunt or from king to queen, for example. Okay. Similarly, if I do a vector from the word Paris to the word France, I should be able to get a similar vector from Berlin to Germany, for example. So this structure arises because word embeddings are learned from real-world text data, which captures meaningful linguistic patterns. So as you will see, we're going to use our training data will be text that we collect from the internet or from books or whatever. And this will allow us to capture these relationships. So some key questions in word embeddings is first, how big should the embedding space be? So a higher dimensional space will allow us to capture more nuances between the words, but can also lead to overfitting. As we saw before, a bigger model is not always better at generalization. And the second question is, how do we find this function W? Okay. Typically, embeddings are learned as part of a classification or prediction task, which involve neighboring words. So we look at different methods today, and you will see that all of them include neighboring words and the context where each word is used. So the first attempt to learn word embedding, essentially, it involves taking a small window of text, say for example 5 words from a meaningful sentence. Okay, for example, one of the best places. Okay, and then change one of the words in this set of 5 words. So here we're going to change the word the with the word function. Okay, by replacing the words randomly like this and training the model to classify the sentences we generate as valid versus invalid, so simple tags, valid versus invalid, we force the network to learn, or the model to learn, meaningful word representations. So in that case, embeddings can be stored as lookup tables or learned using recurrent neural networks, for example. Now, predicting words using context, one of the most famous approaches is word-to-vec, essentially. So in this case, we have 2 versions. We have CBOW, which is continuous word bag of words, and the skip gram model. So these methods are both efficient and scalable, making them some of the most popular ways to learn word embeddings. So let's discuss each of them in detail. So for the bag of words, essentially we get rid of word order. It's used in discrete case using counts of words that appear. So essentially it's gonna take embedding vectors of n words before target and n words after the target, and removes the target word. And then the idea is the network has to find a meaningful representation to guess that missing word. So if you look at the previous slide here, let's say we take that sentence we had earlier, which is one of the best places, and we hide the word best. So we say one of the places, and our target word here that we use for training is best. So we're going to put the one hot encoder for the word one, and then a one hot encoder for the word the, and then the next word, and so on. And this will be our input layer. We'll get into our neural network, and then the neural network or the hidden layers will come up with an output, which the output is also typically is going to be softmax layer, which essentially is supposed to minimize the loss by identifying the correct one hot vector for the word best. Okay, so of course the one hot vector size will depend on the size of our dictionary, how many words we're embedding essentially. And by repeating these training steps over and over again, the network will start to learn then to guess what's the missing word given a bunch of words. And our embedding vector is a vector that's output from the sum block just before we apply our softmax. So that would be the embedding vector with the size that we determine. So here's another example. So for example, the cat sat on the floor, and here our target is the word sat. So again, we're going to use the input is going to be the one hot encoding of the word the cat on floor. We feed this entire input vector into the neural network as the input layer, and then the target is sat in that case. So here's a better graph of this process. So you have the index of cat in our vocabulary. So the vocabulary is already defined from the size of our dictionary. So let's assume you have 10,000 words, for example, as a dictionary, and the word cat is number 2. So that's the one hot vector for the word cat. This is the one hot vector for on, and then you have the rest of the words. And then all this feeds into a hidden layer, and the output layer should be predicted. The correct answer is the word sat, which is this position, for example, in the dictionary. So the network will have to learn the weight W and W prime in order to guess the correct one hot encoded vector at the output here. Now, the dimension of the hidden layer, that's the dimension of the embeddings that we're going to end up using. So once the network is trained, then we can use it to generate embeddings for any word, essentially, right? Because we will feed that word in, and then we will get an embedding vector as a result from this network. So some interesting results when you apply this process is that you can actually predict word analogies. So for example, look here, this is an embedding vector with just 2 dimensions. You can see that king, for example, has the embedding vector 0.3 and 0.7, man is 0.2 and 0.2, and woman is 0.6 and 0.3. When you do king minus man and then you add woman, typically you should expect to end up with the queen, which ends up being true. So there is a linear relationship in this embedding space that we can discover. For example, here you can see the word analogies. Again, each city corresponds to a specific capital of a specific country. So Lisbon to Portugal, Madrid to Spain, and so on. So you can see that the vectors are almost parallel and almost the same length between these pairs of words. Now the second approach is what's called skipgram. So this one, we start with a single word embedding and try to predict the surrounding word. So this is a much less well-defined problem than word2vec that we just discussed, but it actually works better in practice. So let's see how it works. So in this case, we start with a word. So we have, again, our input vector is one hot encoded vector with just one word. And then we have hidden layer, linear neurons. And the output layer, in this case, softmax classifier, gives you the probability that the size of the output layer here is the size of your dictionary. It gives you the probability that each word in the dictionary will be close to that input word. So essentially, what's the probability that the word ability will be close to this input word right here, or the word able will be close, and so on. So by applying this process, we can end up, again, if we have a vocabulary of 10,000 words, and we decide that our embedding vector will have 300 features. So the hidden layer in that case is going to be represented by a weight matrix of 10,000 row times the 300 features that we're talking about. So you have a hidden layer of 10,000 by 300 features, and you end up with the lookup table, which is essentially will tell you the probability that each word is near that target word that we have. So skipgram and the bag of word intuition is that similar context will lead to similar embeddings of two words. So one way for the network to output similar context predictions for these two words is if the word vectors are similar. So if the two words have similar contexts, then the network is motivated to learn a similar word vector for these two words. And last lecture I mentioned this project I was working on, which was essentially given the text description of a given food product, we were trying to find the diet type associated with it, non-GMO, low-fat, kosher, things like that. So by using this approach, we can essentially get an embedding vector for the product description or the ingredients of the product, and an embedding vector for the diet type, and then using a distance measure, for example, like cosine similarity or any other distance measure, we can determine how far is the product from that specific diet type. And by doing that, testing pairs of product titles and diet type, we can end up with very high confidence labeling products, even though we don't really know, or the seller doesn't really state that it's non-GMO or organic or anything like that. But if we use an embedding transformation like this, we're able to find very close relationships that we can generalize from. So some of the problems of word2vectors is that 10,000 words is really small. Okay, so already with 10,000 word and this 300 dimension embedding vectors, that's already a huge parameter space to learn. So imagine how many training examples you would need to learn this parameter. So it's very slow to train and needs lots of data, particularly for words that are not very common. Some improvements include, for example, treat common word pairs or single phrases as words. So instead of doing it by word, you can do it by pair. Okay, so the timing is going to run out, so I'll see you in the next part.